Hey folks, welcome back to part 2 of the helium shortage. Do you remember our discussion of quantum mechanics from last time? We talked about 2 big ideas. The first was anything that can happen probably will happen given enough time. And the second one was that particles are always seeking out the lowest possible energy. Now, these aren't the main ideas of quantum mechanics, and they're not even fundamental ones. They're just really important implications for what we're talking about. In part 1, we talked a lot about bonds, covalent or chemical bonds, and nuclear bonds. Despite having way different binding energies and way different components, all the bonds that we discussed had the same idea in common. They reduced the energy of the particles that were bound together. I've struggled for a way to come up with a description of these kinds of bonds that's faithful to the physics while also intuitive to explain in a short amount of time, and I gotta say I've failed. For chemical bonds, chemistry might tell you that 2 atoms are sharing electrons, but what does that really tell you? I mean, really. The fact is, the details, the physics of bonding, be it chemical or nuclear, involves a lot of quantum mechanics, and the details are really important to their description. I can't just paper over them without making some really terrible, dysfunctional analogy, and I'm not going to do that. If you want to get a sense for what the details are like, Hyperphysics has a really good one-pager on chemical bonds that I'll put in the show notes and was sent out in the notes on Sunday. But be warned, it's a little technical. Otherwise, we'll just keep it simple. Bonds form because it lowers the energy. But here's the thing, sometimes these bonds break because it lowers the energy too. And that might seem like something of a contradiction. But, as with all things in the universe, perspective matters. Whose energy are we talking about here? Last time, we said that there's something really special about helium-4, especially its nucleus. To really understand how special it is, we're going to need to go to the other end of the nuclear spectrum. We're going to compare the binding energy of a uranium nucleus with a helium nucleus. And to do that, it'll be helpful to have a physical picture in mind. Imagine that you're walking your dog at the bottom of a big snowy hill. You've got a ball with you, and you throw it at the hill. The ball hits the hill and rolls back down, and your dog runs after it. Each time you throw it higher and higher and higher. And of course, the ball rolls back faster and faster and faster. This is just gravity at work, so hopefully that's familiar to you. The ball is just trying to roll down the hill, just trying to reduce its energy. And it's not even quantum mechanics. It stops, of course, because of friction. Or because your dog finally catches it. But let's say you keep throwing it higher and higher and higher. Eventually, you throw it so hard and so high that it hits the top of the hill, and it doesn't come back. Weird. Well, it turns out there's an old well at the top of the hill, and your ball has fallen inside. Bummer. As a human, you probably know that you're not going to get your ball back. Poor dog. But, hey, that's macroscopic life for you. But microscopically, things are a little different. When you get small, like really small, like particle physics small, the world is a little counterintuitive. The analogy of the ball, the hill, and the well carries over directly when we enter the microscopic world of quantum mechanics. You can throw a particle up the hill, it will come back down. But if you throw it into the well, way up there, what happens? Well, frankly, not much. The particle just kind of buzzes around inside the well, trapped. But every once in a while, depending on the details of the well and the hill and the ball, the particle will just pop right out through the hill. This phenomena is called quantum tunneling, and particles tunnel out of traps to get to a lower energy state. It's kind of crazy and it's counterintuitive for sure, but it can happen, so it probably will happen given enough time. Now, why quantum tunneling happens is another question for another day, but it can happen. And as it turns out, helium-4 is one of nature's best tunnelers. Really big nuclei, like the biggest ones that are naturally occurring, like uranium or thorium, are kind of a mess. They look like blobs, and in a sense they're kind of disorganized. They're a little too big for their own good. They're still pretty tightly bound together, but if you were to hit one with a neutron, say, then they would shatter into 2 or more pieces. Sometimes, on rare occasion, they break apart on their own, spontaneously. We call this radioactive decay. Radioactive decay is a secondary effect. It's a quantum mechanical effect. It's sniffing out the lowest energy state for at least some of the particles involved. Here's a way to think about the decay of a big honking nucleus like uranium. Sometimes clusters of particles within a nucleus are bound a little more tightly. That cluster might bounce around in the nucleus, banging against the surface from time to time, until sometimes, accidentally, it finds itself just a little too far away. At that point, it breaks away from that residual nuclear stickiness, and the electrical repulsion of all those protons takes over, and the cluster gets rapidly pushed away. This is quantum mechanical tunneling in action. As per our analogy, the ball is a pair of protons and a pair of neutrons. In other words, a helium-4 nucleus. The hill is the electric field given off by the big uranium nucleus, or the remnant thereof. And the well, that's the nuclear force, the stickiness on the different protons and neutrons. From the perspective of that pair of protons and neutrons, that helium-4 nucleus, it's tunneling out of that big honking uranium nucleus to get away from that electric field, to lower its energy. Now, from our perspective as humans, it's like that big nucleus just emits a particle, emits some radiation. There are different kinds of radiation from different kinds of physical effects, but the one that we just described here for historical reasons has been called alpha radiation. And the pair of protons and neutrons is called an alpha particle. But it's just a helium-4 nucleus. So finally, after all of this talking, and after all of these little cartoons, we finally understand where helium comes from. It comes from the radioactive decay of really heavy elements. Great, but in practice, where do you go to find it? Have you ever been to a big party in a big auditorium? Or maybe outside in a pavilion? Where do all the balloons that kids accidentally let go wind up? Yeah, exactly, the ceiling. And that's the big insight. You see, we can collect helium when it's trapped underground. Helium is mined together with natural gas. When you drill through the capstone of the Earth's crust, all the gases in there, including helium, are released. As we tap more and more of these gas wells, we're basically popping all of our sources of helium. Of course, not all natural gas wells are going to have a lot of helium to provide. Some are going to have more than others. And as it turns out, those that are located near big deposits of uranium and thorium are going to have a lot more helium to provide. Like natural gas, there's a huge international market for helium. Because helium is inert, it doesn't interact chemically with other substances, it's strongly preferred for industrial applications. Helium is used whenever you want to avoid exposure to other elements like the air. For example, welders will use helium as a shielding gas to prevent any air or water vapor from attaching itself to the weld and damaging it. Shipbuilders will use helium to detect leaks in the hull of a ship. And MRI machines, that is magnetic resonance imaging that you use for a lot of medical purposes, use helium in a really interesting way to cool down their superconducting magnets that allow them to generate these huge magnetic fields. That story of that technology is really fascinating in and of itself. It's a totally different direction, and it's worth looking up. But for reference, older MRI machines used to go through something like 2,000 liters of helium a month, which is a lot. But apparently, newer machines on the market now have become a little bit more efficient, a little bit more tight, and they can run at 300 to 400 liters of helium per month. Other scientific research equipment uses helium in this same way to generate really strong magnetic fields by superconducting magnets, including the Large Hadron Collider in Europe, which is 27 kilometers long and has an enormous number of magnets. It's an enormous consumer of helium. Rockets will also use helium to clean out their fuel tanks, which are primarily, for oxygen gas or hydrogen gas, to make sure that there's no other contaminants in the fuel tank itself. And of course, we use helium for balloons. The demand for helium has grown with a lot of these new technologies, and the market for it has been rocky, to say the least. The helium stores that are caused by radioactive decay build up underground, but they take millennia to get to an appreciable amount. So, in a very real sense, helium is a non-renewable resource. It's also not a particularly ecologically friendly one. Over the past 20 years, there's been 3 major supply shortages of helium, and we're just coming out of one now. Now, most of these are caused by, international disputes and kind of other similar problems, but a big driver of that of late has been hydraulic fracturing, which looks for natural gas trapped in shale rock, which means that they're not popping gas wells really at all. Historically, the United States has been a dominant producer of helium. And indeed, to that end, way down in Amarillo, Texas, there's this huge underground formation, like a big cave, where they used to just stuff a whole bunch of helium to store under there. And it was called the Federal Helium Reserve. And the idea behind it was they would use it as a market buffer to kind of soften the giant swings of supply and demand in the market. But unfortunately for everyone involved, at some point years ago, Congress elected to sell all of our remaining strategic supply of helium at really fire sales prices, really, really low prices, which ended up creating a huge supply glut, which was great for a lot of the technologies that were coming online. But what that ended up doing is creating a huge demand for which there was not enough sustainable supply. So starting in around 2018, there was a lot of trouble getting enough helium to enough folks, and that's turned out to be kind of a huge problem. If you don't have the helium necessary to cool down the magnets associated to your MRI, you could actually severely damage these multi-million dollar pieces of equipment. Fortunately, efforts on the consumer end to acquire more efficient machines, to develop a helium kind of recycling circular systems, as well as the economic downturn associated to the COVID-19 pandemic, has brought the demand for helium back to a manageable level. And so we're actually coming out of that helium shortage now. These days, more and more gas wells are coming online, not just in the United States, but also especially in Algeria and Qatar, and even Siberia. So the helium market is kind of entering a new phase now, where it's very diversified and very international, which I guess we'll see what that means for the prices and for the market swings. So from a nuclear physics perspective, or from a technological perspective, or from, macroeconomics or international trade, our lives are more bound up with helium than really ever before. But of course, there's more to the story. That slow, natural production of helium has a lot more to do with our experience and even our lives here on Earth than you might think. Last time, we talked a lot about density. Density matters. Heavy stuff sinks, light stuff floats. And the same is true about heavy elements. Heavy elements like uranium and thorium sink into the Earth. Of course, these are solids we're talking about, rocks, so it takes a really long time, geological time, for that to happen. But suffice it to say, there's a lot of uranium and thorium deep in the Earth left over from its very formation. Now, deep inside the Earth, these elements decay. They convert nuclear binding energy into particle motion, to motion energy, into, in other words, heat. Incidentally, that's how nuclear power plants work. They boil water through radiation heat, and that water vapor turns a turbine and generates electricity. Scientists have estimated that about half of the Earth's internal heating is caused by radioactive decay. And almost all of that radiation is generated by alpha decays of uranium and thorium. And of course, the Earth is huge, so that's a lot of heat being generated. What do you think happens with all of that heat? Where does it go? What does it do? Well, it melts rock and drives thermal convection, which results in a process that we've come to know as plate tectonics. Yep, that's right. Earthquakes, volcanoes, all that stuff is powered by radioactive decay. That's the same radioactive decay that over thousands of years generates helium. That's the same helium that's in your balloons. Crazy, right? But that's not the end of the story. That same heating in the Earth is believed to cause the Earth's magnetic field. You see, all that convection, all that swirling, that internal heat is believed to turn a giant ball of iron deep in the Earth's core, which effectively acts as a magnetic dynamo generating the Earth's magnetic field, which we use, for example, to navigate with a compass. Now, it's not a terribly strong magnetic field, but it is terrible in scale, humongous. What's more, that magnetic field, which is driven by radioactive decay, actually protects us from radiation coming in from space. You see, the sun is shooting out particles at us all the time, charged particles that would be really damaging. It's called the solar wind. But the Earth's magnetic field traps those particles. So instead of colliding with us, they ricochet around in the sky, in the upper atmosphere. And as they bounce around, they pick up a little bit more and more heat. And as they get more and more energy, they begin to glow. That glow, that plasma of particles coming in from space that are trapped in the magnetosphere, is what we've come to know as the aurora. All of this beauty, all of this protection from radiation, all of this terrible power of earthquakes and volcanoes and the movement of continents are all driven by the production of helium. Who knew that such a humble, small, inert gas could be responsible for so many effects, so many aspects of our daily life, of our very existence?